Example 146. In 1995, the American Cancer Society randomly sampled 1,500 adults, of which 555 smoked. In 2005, they surveyed 1,750 adults and found that 578 of them smoked. Form a 90% confidence interval for the difference between the proportion of smokers in 1995 and 2005. Has the proportion decreased over the 10-year period? All right, so this problem we did as a hypothesis test, and we showed that it did decrease. So what we're going to do now is to do a confidence interval to run a similar kind of test. Okay, so let's start with the beginning of the problem, which is the data step. So for the data step, I'm going to copy down the 1995 data first. That's only because they gave it to me first, but it's a perfectly fine order to do things in, so we're going to go and do that way. So the 1,500 goes first, and then the number of people who smoked is 555 in that year. And then in 2005, they surveyed 1,750 adults, right? And among that group, they said 578 of them actually smoked, right? So out of 1,750, 578 of them smoked. Okay, and then from there, we have a confidence level, which is given as 90%, and that corresponds to an alpha level, which is 0.10 or 10%. Okay, so we have some given data. The next things we need to do to have enough to form our confidence interval is we need to come up with the p-hats for each of these and the q-hats for each of these. Remember, we didn't need q-hats for the sample data before in hypothesis testing, but we do need them now for confidence intervals. So we'll have 555 divided by 1,500. And then for the next one, we will have 578 divided by 1,750. So let's work out those and see what we come up with. Okay, so we have 555 divided by 1,500, and that produces an answer of 0.37. And we'll do the same for the next one, which is 578 divided by 1,750. And if I remember correctly, this was 33%. Yes, so 0.33, and then it would go 0.3, but we'll just leave it as 0.33 there. Okay, so that's good enough. Now, from there, once we have the sample values for p-hat, we need to come up with q-hats. And again, these values we did not need in hypothesis testing because we used actually a pooled estimator, if you remember. So we used a q-hat, but it was connected to a pooled estimator for the proportion p-hat. We don't have those things anymore. So let's just fill these in. We don't need any special calculations. You know, it's 1 minus 0.37 here, right? So the answer then for this one is going to be 0.63. And for this one, it's going to be 1 minus 0.33. So the answer, of course, will be 0.67. Okay, so now that we have all of that set up, our next step is to take these numbers, the p-hats, the q-hats, and the n's that we have, and we're going to plug them into our margin of error formula. But before we can do that, we're going to need one extra value. This is from the table. Is our critical z value, z alpha divided by 2. So z alpha divided by 2, remember the alpha here is 10% in this problem. We always use z when we're working with proportions, right? Because we're using the normal distribution to approximate the true distribution. And so we'll have the z value. We have alpha is 10%. Confidence intervals are always alpha divided by 2. So that 10% will be reduced to 0.05 once we divide it in half. And then we're going to go to our t-table and we're going to look up this 0.05 and one tail, go straight to the bottom and find the corresponding z-score that's associated with that. Okay, so we're looking in the 0.05 column here, and then we're going to go straight to the bottom until we find our corresponding z-score. So let's do that. We look down here, we see it's 1.645. 1.645. Okay, so we found the answer to be 1.645. So that's our critical z value. Now that we have that number, we're going to take it and plug it into our margin of error formula along with everything else we already used, right, or found. Okay, so the margin of error formula, if you recall, is z alpha divided by 2 times the square root of, and this square root is going to be pretty straightforward here. It's p hat times q hat over n, but each one of these is 1, 1, 1. In other words, for the first group, 1995, for example, plus p hat q hat over n again, but this time it'll be 2, 2, 2, right? Because it'll be the second group, or the 2005 group. All right, let's plug in these numbers and see what this comes out to be. It'll be 1.645 for the z value, times the square root of the p hat q hat pair for the first group is 37 times 0.63. And that'll all be divided by the n being 1500 in this particular case. And then it'll be plus, and we'll have another p hat q hat pair, that's 0.33 times 0.67 this time, divided by 1750. Okay, now let's take that and figure out what that gives us. Okay, so 1.645 times the square root of, and then remember these fractions don't need any special parentheses or anything, it's just 0.37 times 0.63 divided by 1500 plus 0.33 times 0.67 divided by 1750. Close up your parentheses when you're done, hit enter, and you get 2.7% approximately. So the error here is going to be approximately 0.02761, let's say. So just round it off a little bit. That's your error. I'm just going to store mine in the calculator for use later. And let's go up to the top and finish this up now. So we're going to need to subtract our two sample proportions. We're going to do it in the order in which we found them, right? So we're going to do p1 hat minus p2 hat minus the error, comma, p1 hat minus p2 hat plus the error. Okay. So let's go ahead and do that in our calculators then. The difference here we can do quickly, and then we'll just put the error in afterwards. 37 minus 33 is 0.04, right? Minus the error, which we said was about 0.02761, and then 0.04 plus 0.02761. Okay, and then let's just finish that up now since we have that all set up. So 0.04 minus our error, and then the same thing, but plus the error this time. When you're done, you get 0.012 up to 0.068. And remember what we're saying here. We are 90% confident, right? 90% confident. The true difference, and that difference is what here? Remember, it's the row for 1995 minus the row for 2005. Remember, that's how we did the subtraction. That's the order we placed our numbers in, right? So we are 90% confident that the true difference is inside the interval. Okay, what does that mean to be inside the interval? Well, the interval is entirely positive. So what does it mean when the interval is entirely positive? It means the first value is larger in this difference. So we're saying that there's a statistically significant difference between the proportion of smokers in 95 and 2005, and that difference is that 1995 had a higher proportion of smokers. Remember, if it's all positive, the first one is bigger. One more thing that I haven't mentioned that much here, but I want to make sure you understand here what this interval is supposed to contain. It contains the true difference, right? So we know there is, according to the idea that they're both positive, we know that 1995 had a higher proportion of smokers. So the question might be, well, by how much was it higher? Well, this interval is giving us possible values for the difference, right? So it's saying, well, it could be as high as almost 7%, right? 6.8%. So it could be as high as a 6.8% difference, meaning that, 6.8% more people smoked in 95 than in 2005. Or it could be as small as a 1.2% difference, or some number in between those two, right? That's what the interval is basically telling us. Okay, so that's your interval. That's your conclusion, that more people smoked in 95, or a higher proportion of people smoked in 95 than do in 2005.